Actually, these are the authors of our joint paper. So this is me, and this is Professor Sun here, right here. Thank you, Professor Sun, for this. And also, this is Professor Kim Chuan Tao from National University of Singapore. And this is Professor Naihua Xiu from Beijing Jiao Tong University, who is also my PhD supervisor. So this is a joint work of our four. And this is the outline of this talk. So first, we will give a very brief introduction about what we're working on. And so actually, we are more caring about high-dimensional data analysis. And we know that the feature selection and grouping is very useful, especially in the high-dimensional data containing some not that important features. So we first adopt this kind of model, which is called OSCA. And in this optimization model, there is a least squares loss term. And with this kind of regularization, the first term here is the L1 norm, and the second term is the pairwise L infinity norm here. So by using these two terms, we can simultaneously encourage sparsity and grouping. And we know that this is also a very special weighted key-find norm from mathematics. And because if you set the corresponding coefficients, then you will see this kind of regularization term is exactly this weighted key-find norm. And also we have read the book, the paper, I think it's Professor Bogdan here. And this paper is published in Annals of Applied Statistics in 2015. So they have introduced this slope model here. And this is a more general case because it can include this kind of L1 norm, this kind of L infinity norm, and also OSCA. So we'll work on this model directly. And here, this kind of slope regularization is also a very special key-find norm here, because here these kind of parameters are required to in the non-increasing order here. And so we already know that statistically, Professor Bogdan has showed this kind of regularizer can control the false discovery rate very nicely. And also, she also found some interesting applications for this kind of model. I guess she will introduce some of them here, like the portfolio selection. And mathematically, this proximal mapping of this regularization term can be computed efficiently based on this kind of power algorithm. And this is for solving the isotonic regression problem in the field of ordered statistics. So if this proximal mapping is efficiently computable, then those first order methods like APG and ADMM can be admissible for some small size or medium size problems. But our focus is how to handle those large scale instances. Here, large means the number of features may be super large. And also this kind of M, the M there, the matrix, the number of rows in the matrix, the number of rows in the matrix M may also relatively large. So that's the motivation for our work. And here, if you want to use some more efficient method from the optimization community, we will think about the second order methods. So we want to dig more properties about this carbon lambda, which is that slope regularizer function. And we know this proximal mapping can be written in this way using this formula, where X lambda is actually the optimal solution mapping of this isotonic regression model. And so here, from Professor Jie Sun's PhD thesis, it has already been showed that this proximal mapping is piecewise affine. So this is a very nice property and will further allow us to design semi-smooth Newton method, because we actually figure out what are those generalized Jacobi of these proximal mapping. And those generalized Jacobi will form a set of matrices like this. Here, M is a symmetric matrix taking a form like this. And here, pi is the involved find permutation matrix. And here, this capital P here is actually Jacobi. We call it now HS Jacobi because this kind of work has been done by Professor Jiye Han and Professors Sun here. So we use this kind of formula, then we can write out the generalized Jacobi of this proximal mapping function. And this is more technical here, so we'll skip the details. And also, this piecewise affine property for this proximal mapping and actually leads to the semi-smoothness. So now actually we can prove that this proximal mapping is gamma order semi-smooth for any positive gamma. And this nice property allows us, or we can say guarantee, the superlinear or even quadratic convergence when we perform semi-smooth Newton method. So this is a very nice property. And here we'll introduce the algorithm. So now we are trying to use the augmented Lagrangian method to solve the problem. And because we are focusing on this high dimensional regression setting, which means the number of sample size, which is M, is far smaller than the number of features. So in this case, we will decide to solve the dual problem, which means we will use ALM algorithm to solve the problem from the dual perspective. And so that's going to be the primal problem, and his dual will take the form like this. And here we have adopt the conjugate for the original slope regularizer here. And we can first write out his augmented Lagrangian function and try to reduce the number of variables. So we take the infima over epsilon. So epsilon is actually here. So that's actually a variable for the dual problem. And we have to eliminate this guy by using this kind of Mori-Yoshida regularization of these conjugate function here. And so we will perform this kind of augmented Lagrangian method. And this is the traditional framework of ALM. And you will see here to update the variable y, which is actually the main task in this algorithm. And this is the essential subproblem. So we will use the semi-smooth Newton method to solve this subproblem and to update the multiplier. And this multiplier is actually the decision variable for the original primal problem. And we use this proximal operator here. And you will see if you look at this algorithm from the primal perspective, this is the PPA. So actually you can look at this algorithm here. The outer loop is kind of PPA for the primal problem. And now we are trying to figure out how to solve this subproblem more efficiently. So we are trying to use semi-smooth Newton method because here the involved objective function here has some nice properties. And these are some stopping criteria we use for solving this subproblem. And now, the first we have to consider about the convergence of the augmented Lagrangian method. So we know that if this problem has some error bound condition like this, then the augmented Lagrangian method will certainly have this kind of asymptotically superlinear convergence, which means some fast linear convergence actually. And so we can easily obtain this global convergence because we are using ALM algorithm for this nice problem here. And we can also achieve the local linear rate convergence and also global linear rate convergence by using those error bound condition. And so the main issue tends to be how to solve the subproblem efficiently, because we are using the second order method. That means in the common sense, you may think one iteration will be costly. So actually, we will show you that even we perform this second order method, the cost will be similar to the first order methods. So we work on the subproblem and use first order optimality conditions. So that's going to be the gradient equals the zero vector. And we know this is not smooth anymore, but we can actually characterize his generalized Jacobi. And we have already discussed it. This will take the form like this. So in this case, we can use semi-smooth Newton method to solve the this essential subproblem here. And here, so the difficulty is how to choose VJ and how to solve this corresponding Newton equation efficiently, especially for some large scale cases. And if you look into this kind of equation, you will see the size is actually m by n. So if the m is not that large, we can solve this linear equation directly. And if m is relatively large, then we can use like conjugate gradient method to solve it approximately. So, and we can also use some step size rule to find a suitable step size here. And so that's the algorithm 2, which is designed for solving the corresponding subproblem. So here, VJ is like this, an identity matrix plus this kind of term here. And MJ takes form like this. So we can dig more and find that this matrix P can be written by using two matrices. The first matrix H will take the form like this. You have some zero blocks, you have some identity blocks. And you here will have this kind of structure. So you have some blocks, some of them, so in a column, some of them take the same value and the others will be zeros. And here the capital N is actually those groups of blocks there, and which is smaller than the original number of features. So this U is actually has less columns than his rows. And so we can see these kind of sparse and low rank structures has been involved in this matrix P. And this P is actually from the generalized Jacobi of those regularization, or you can say proximal mapping of that special function. And that special function actually is something due to the sparsity of the original variable x and some group structure of that variable x here. So we can get this kind of sparsity in this second order information. And so we call it the second order sparsity. And moreover, if you perform this kind of matrix multiplication, we can reduce the computation cost further if you dig more about these sparsity involved. So the reduction of the cost for computing this part will be very significant, because this is kind of from this order to this order here. So if N is super large, while R1 and R2 are actually no more than the sparsity of the vector X, that means the non-zero components in the vector X here. So if this is very small, then this reduction is actually dramatic. And that's why our method will perform very fast. So we also do some numerical experiments to illustrate this kind of high efficiency about our algorithm. And we use this kind of stopping criteria, the relative duality gap and the dual infeasibility. And so here, this dual infeasibility is actually this kind of is coming from this indicator function here. And this indicator function is actually the conjugate function of, the conjugate function of the original regularization function here. And we also use these following termination rules. So we set the tolerance to be 10 to -6. And we also set up this kind of maximum number of iterations to be 50,000. So once the iteration number reaches this guy, then we will stop the algorithm. But actually you will see the iteration number for our algorithm is quite small. And we also use this relative KKT residual to measure the solution accuracy of those algorithms. And for comparison, we compare the ADMM, which is a typical first order method, and also APG. And this APG is implemented by the slope package. So from Professor Bogdan here. And so A1 is the ADMM, A2 is the APG, and A3 is our algorithm. And these are the problems we are testing. And you will see here, for all these instances, M is smaller than N. So we have more features and we have less samples here. And these are the comparison results. So we have tested 15 problems. And each of them, we used 3 different parameters here. So here, this A is actually W1 is aligned to be like this. And actually for this numerical part, we just test the Oscar model because in slope model, there are many parameters to be determined because we have n lambda I there. So we simply choose the Oscar model for testing. And so we actually have 45 testing instances. And these are the corresponding comparison results. So here, this NNZ means the number of non-zero components. And this eta is about the residue, the KKT residue. And this is the computation time. And this is the iteration number that has been used. So here, for example, for P3, you will see this accuracy is actually very high. And the computation time here, so A3 is our method, is actually much faster than these 2 first order solvers. So, and you will see this iteration number here. We like 20 or 40 or 13 or 40, this kind of level of iteration numbers. And similarly for the other testing instances. So actually all these tested instances we have solved successfully, which means for solving every instance, they have achieved the required accuracy, which is 10 to -6. But some of them will not be solved successfully by these 2 first order methods, like ADMM, they have 3 failed. And for slope, which is APG, so there are 22 cases that has been failed. So in this case, we can simply conclude that our method has high accuracy and high speed. Actually, for some of them, our methods are 100 times faster than those 2 first order solvers. We also plot this kind of performance profile. So in this graph, you can see the this kind of horizontal axis means the at most X times of the best. And this kind of vertical axis means the percentage of the problems that has been successfully solved. For example, if you take 150 here, that means if you give 150 times of the time of the cost or the time of the best algorithm, then for this kind of slope, this kind of APG, they still have 40 40% of those test problems which cannot be solved successfully. So you can see here, this is like 80%, this is like 90%. So still 10% of ADMM. And you will see here, this is like 0.6. So it's like 40% of the tested instances which got not successfully solved. And also we have tested this kind of microarray data here. And we draw this kind of partial solution path. We connect all those first 10 largest coefficients in magnitude. And you will see about all of these three algorithms will give us the similar results. But if you see the computation time, and we found that our method is like 11 times faster than ADMM and like 40 times faster than slope. So that means the time efficiency is very obvious for our second order method. And I think that's all for my talk. So theoretically, we have dig more properties about the proximal mapping of the slope regularizer function. And based on it, we can then design the second order method, which is called the the semi-smooth Newton-based Augmented Lagrangian method to solve these kind of slope problems, and especially on Oscar model. And the numerical experiments can illustrate the high efficiency and the robustness of our method. Okay, I think that's all for the talk. And at the end, I want to make an advertisement. So actually, our group and also Professor Sun have given us great support about a series of international conference on statistical optimization and learning. And right at this end of week, we will hold this 6th international conference. So actually, our group will be very happy to work with people from statistics and machine learning, and your support will be very helpful for us. Okay, so that's all for my talk. Thank you so much.